Welcome to this coding walkthrough. In this session, we'll explore problem number 958, check completeness of a binary tree. This problem challenges us to verify whether a given binary tree satisfies the properties of a complete tree. We'll break it down step by step, examine different approaches, and analyze their complexities. Let's dive in. Here, we are tasked with determining whether a given binary tree is a complete binary tree. Recall that in a complete binary tree, every level except for possibly the last is completely filled with nodes, and the nodes on the last level must be aligned as far to the left as possible. The input to the problem is the root of the binary tree, where each node contains a value, a left child, and a right child, both of which can be null if no child exists. The output is a Boolean value, true if the tree satisfies the conditions for completeness, and false otherwise. To make this more concrete, let's look at an example binary tree. In the first example, the input binary tree has the structure shown, where the root node has a value of 1, with 2 children, 2 on the left and 3 on the right. Node 2, in turn, has 2 children, 4 and 5, while node 3 only has a left child, 6. The output for this example is true because this tree satisfies the conditions for completeness. All levels except the last are fully filled, and on the last level, nodes 4, 5, and 6 are positioned as far left as possible. However, not all trees meet this criterion, as we'll see in the next example. In the second example, the binary tree structure is similar at the top level, but node 3 has a right child, 7, without having a left child. This tree is not complete because the last level is not aligned as far left as possible. Node 7 is positioned on the right, leaving a gap where its left sibling would be. On the other hand, in the third example, we have a much simpler tree with only 2 nodes. 1 is the root and 2 is its left child. This tree is complete because all the levels are fully filled where applicable, and the last level satisfies the condition of being as far left as possible. To summarize, the problem has some constraints and edge cases to consider. The tree can have up to 100 nodes, and each node has a unique value between 1 and 10,000. A node can have either 0, 1, or 2 children. For edge cases, a single node tree is always complete, as is a tree where all nodes only have left children. However, a tree where nodes only have right children is not complete. Sparse nodes in the middle of the last level also invalidate completeness. A key observation is that completeness is tied to the positioning of nodes, and level order traversal, or breadth-first search, is an effective way to ensure that all nodes in the last level are as far left as possible. During traversal, encountering a null node means that all subsequent nodes must also be null for the tree to remain complete. To determine if a binary tree is complete, we can start with a brute force approach that leverages a level-by-level traversal. The intuition here is based on the definition of a complete binary tree. Every level except possibly the last is fully filled, and the nodes of the last level are aligned to the left. To implement this, we use a breadth-first search, or a level-order traversal, and verify these conditions explicitly. During the traversal, we maintain a flag called end. This flag is triggered when we encounter the first null node, indicating the start of the end level. If we find any node after this null node, the tree does not satisfy the completeness condition. On the other hand, if the traversal concludes without breaking these rules, the tree is complete. This method is efficient, with a time complexity of O(n), since we visit each node once, and a space complexity of O(n), due to the use of a queue for the traversal. While the brute force approach is straightforward and aligns closely with the problem definition, it has its trade-offs. Specifically, the space required for the queue can be significant for wide trees, especially at the last level. An alternative to this is an optimized approach that uses a numbering scheme. The key intuition here is that in a complete binary tree, nodes can be assigned indices like a 1-based array. If the tree is complete, the total number of nodes will match the highest assigned index. To implement this, we again use a breadth-first search. Each node is assigned an index based on its position, where the left child of a node gets 2*i and the right child gets 2*i plus 1. Throughout the traversal, we track 2 values, the total number of nodes and the maximum index encountered. If these 2 values are equal at the end of the traversal, the tree is complete. Like the brute force method, this approach has a time complexity of O(n) and a space complexity of O(n), but it provides a more structured and mathematical way to verify completeness. The numbering scheme is an efficient and elegant approach, but it's not the only alternative. Another method uses a recursive depth-first search to verify completeness. This approach is based on the recursive definition of a complete binary tree. If the left subtree is full and the right subtree is complete, then the entire tree is complete. Using this divide and conquer strategy, we first compute the depth of the tree, which helps us evaluate the completeness conditions at each node as we traverse recursively. While this method is elegant, its trade-offs include a higher risk of stack overflow for deep trees and less intuitiveness for beginners. It also has a time complexity of O(n), but uses O(h) space for the recursion stack, where h is the height of the tree. For these reasons, breadth-first search methods are generally preferred for completeness checks, as they are more memory efficient and easier to implement. Ultimately, the strategy we chose was the brute force approach based on breadth-first search with early null detection. This method aligns directly with the problem's definition of completeness, making it conceptually simple and easy to debug. It avoids the additional overhead of calculating indices or managing recursion stacks, which makes it more robust for large or unbalanced trees. The key insight here was recognizing that encountering a null node during BFS signals the start of the tree's final level, allowing us to immediately verify the completeness condition. This ensures efficiency by avoiding unnecessary checks. While the optimized numbering scheme is mathematically elegant, it introduces complexity that's unnecessary for this problem. Similarly, the recursive DFS approach, though compact, is less memory efficient and harder to implement. Our chosen strategy strikes the right balance of simplicity, clarity, and efficiency, achieving a final time complexity of O(n) and space complexity of O(n). In this problem, we are tasked with determining whether a given binary tree is a complete binary tree. To recall, a binary tree is considered complete if all levels except possibly the last are fully filled, and nodes in the last level must be left aligned, meaning there cannot be any gaps between nodes. To solve this, we will use a breadth-first search, or BFS, approach, traversing the tree level by level. While traversing, we check two key conditions: if a null node is encountered, no non-null nodes can appear after it, and all levels before the last must be completely filled. The algorithm begins by initializing a queue to facilitate the BFS traversal, adding the root node to the queue. If the root itself is null, then the tree is trivially complete. We then process nodes level by level, inspecting their children as we go. Now, during the traversal, we examine the left and right children of each node. If the left child is non-null, it is enqueued for further processing. If the left child is null, we set a flag indicating that a null node has been encountered. For the right child, we enqueue it only if no null node has been encountered, otherwise, the tree violates the completeness condition. If the right child is null, we set the same flag as we did for the left child. A crucial part of this algorithm is detecting violations. If any non-null node is encountered after the null flag is set, the tree is not complete. Common edge cases include single-node trees, trees where all levels except the last are full, and skewed trees that lean entirely to the left or right. Finally, if we traverse the entire tree without detecting any violations, we can conclude that the tree is complete. To support this approach, we utilize two key data structures. First, we use a queue to perform the level order traversal. The queue ensures that nodes are processed sequentially, level by level, which is critical for verifying completeness. Second, we use a Boolean flag to track whether a null node has been encountered. This flag is instrumental in ensuring that no non-null nodes are processed after a null node, maintaining the completeness rule. BFS is especially suited for this problem because it guarantees level-by-level processing, allowing us to easily check the alignment and fullness of each level. The flag serves as an efficient mechanism to enforce the rule that no further non-null nodes can appear after a null. In terms of complexity, this algorithm operates in O(n) time, where n is the total number of nodes, as each node is enqueued and dequeued exactly once. The space complexity is also O(n), due to the queue storing nodes at each level. There are also optimizations we can make to improve the algorithm's efficiency. For instance, we can stop the traversal as soon as a violation is detected, exiting early to save unnecessary processing. Additionally, the use of the null flag itself is an optimization, as it reduces redundant checks for completeness. Let's explore an example to see the algorithm in action. Consider a tree with the following structure. The root node has a value of 1, with left and right children 2 and 3, respectively. Node 2 has children 4 and 5, while Node 3 has only a left child, 6. Starting with BFS, we enqueue the root and process it, enqueuing nodes 2 and 3. Next, we process node 2, enqueuing its children 4 and 5. We then process node 3, enqueuing its child 6, followed by a null placeholder for its missing right child. Finally, we process nodes 4, 5, and 6, marking the null placeholder and confirming that no non-null nodes follow. Since no violations occur, the tree is complete. Now, let's examine a slightly different tree to illustrate an edge case. Here, the root node again has left and right children 2 and 3. Node 2 has children 4 and 5, but node 3 has only a right child, 6. Beginning the BFS traversal, we enqueue nodes 2 and 3. We process node 2, enqueuing its children 4 and 5. Next, we process node 3 and enqueue a null placeholder for its missing left child, followed by its right child, 6. However, encountering a null node before a non-null node violates the completeness condition. Specifically, the null placeholder for node 3's left child is followed by node 6, which breaks the rule that no non-null nodes can appear after a null. Therefore, this tree is not complete. Here, we start by importing the Deet class from the collections module, which we'll use to traverse the binary tree level by level. We then define a tree node class to represent each node in the binary tree, with attributes for its value, left child, and right child. Next, we create a solution class and define the method isCompleteTree, which takes the root of the binary tree as input. The first thing we check is whether the root is none. If it is, this means the tree is empty, and we can immediately return true because an empty tree is considered complete. Now, we initialize a queue using Deek and add the root node to it. This queue will help us perform a level order traversal of the tree. We also create a flag, encountered_null, and set it to false. This flag will help us track if we've encountered a none node, which is crucial for determining whether the tree violates the completeness property. Then we enter a while loop that continues as long as there are nodes in the queue. Inside the loop, we dequeue the first element and check if it's none. If it is, we set the encountered_null flag to true, indicating we've found a gap in the tree. If the current node is not none, we check if encountered_null is already true. If it is, this means we've found a node after encountering a none node, which violates the completeness property, so we return false. Otherwise, we enqueue the left and right children of the current node, even if they are none, to continue the level order traversal. Finally, if the while loop completes without returning false, it means the tree satisfies the completeness property. In that case, we return true. This ensures that we've checked all levels of the binary tree and verified that any gaps only occur at the last level and to the right side. By using a level order traversal with a queue and the encountered_null flag, this implementation efficiently determines whether the binary tree is complete. The time complexity of this approach is O(n), where n is the number of nodes in the tree, since we visit each node exactly once. The space complexity is also O(n), in the worst case, due to the storage required for the queue. Here, we begin implementing the solution in Java. First, we define a basic tree node class to represent each node in the binary tree. Each node contains a value, and pointers to its left and right children, which are initialized to null in the constructor. Then, we create the main solution class and define the method isCompleteTree, which takes the root node of the binary tree as input and returns a boolean indicating whether the tree is complete. If the root is null, we immediately return true, as an empty tree is considered complete. Next, we utilize a queue to perform a level order traversal of the tree. We initialize the queue with the root node and introduce a boolean flag, encountered_null, to track whether we have seen a null node during the traversal. Within the while loop, we process each node in the queue. If the current node is null, we update the encountered_null flag to true, indicating that we've reached a gap in the tree. If the node is not null, we check if the flag is already true. If it is, this means there's a node after a null in the level order traversal, which violates the completeness property, so we return false. Otherwise, we add the current node's left and right children to the queue, even if they are null, to continue the traversal. Once the queue is empty, and no violations of the completeness condition have been encountered, we return true, confirming that the tree is complete. To determine if a binary tree is complete, we need to check two key conditions. First, all levels except the last must be fully filled, and second, any nodes on the last level should be as far left as possible. To solve this, we use breadth first search, or BFS, with a queue to systematically traverse the tree level by level. During this traversal, it's crucial to monitor if we encounter a none node. Once a none is seen, no valid nodes should appear afterward. If any non-null node is found after a none, it means the tree is not complete. For example, consider the binary tree shown here. It is a complete binary tree because all levels are fully filled except the last, and nodes on the last level are left aligned. To verify this programmatically, we initialize a queue with the root node and set a flag, encountered_null, to false, indicating we haven't yet encountered a none node. From here, we'll proceed with a step-by-step BFS traversal to check the tree's completeness. Starting the BFS traversal, we first dequeue the root node, 1, and add its children, 2 and 3, to the queue. Since neither child is none, the encountered_null flag remains false. Next, we process node 2, adding its children, 4 and 5, to the queue. Again, no none nodes are encountered, so we continue. Dequeuing node 3, we add its children, 6 and none, to the queue. Although we've now added a none to the queue, it hasn't yet been dequeued, so the encountered_null flag is still false. As we proceed, we dequeue node 4 and add its children, both of which are none. The queue grows with additional none values, but these are expected for a complete binary tree. Similarly, we dequeue node 5 and add its none children, further filling the queue with none values. Finally, we dequeue node 6, adding its none children to the queue. Now, when we dequeue the first none, we set encountered_null to true. From this point on, we only dequeue none values, and no valid nodes appear afterward. Since this condition holds true throughout, the tree is confirmed to be complete, and the output is true. Now let's consider another example of a binary tree, this time one that is incomplete. The structure of the tree is slightly different. While the first two levels are completely filled, the last level has a node on the rightmost side missing, creating a gap. We start the BFS traversal by initializing the queue with the root node, 1, and setting encountered_null to false. Dequeuing the root, we add its children, 2 and 3, to the queue. Both are valid nodes, so we continue. Dequeuing node 2, we add its children, 4 and 5, to the queue. So far, no none nodes have been encountered, and the traversal proceeds as expected. Next, we process node 3, adding its children, none and 6, to the queue. Here, we introduce a none into the queue but haven't yet dequeued it, so the encountered_null flag is still false. Dequeuing node 4, we add its none children to the queue, which is expected for a complete binary tree. Similarly, node 5 is processed, and its none children are added to the queue. At this point, we dequeue the first none and set the encountered_null flag to true. However, when we dequeue 6, we encounter a valid node after a none, which violates the condition for a complete binary tree. This confirms that the tree is incomplete, and the output is false. Finally, let's consider the simplest case, a binary tree with only a single node. Here, the tree consists of just the root node, 1, with no children. We initialize the queue with the root node and set the encountered_null flag to false. Dequeuing the root, we add its children, both none, to the queue. When we dequeue the first none, we set encountered_null to true. The remaining none is then dequeued, and since no valid nodes appear after encountering none, the tree satisfies the conditions of a complete binary tree. Therefore, the output is true. The time complexity of the solution is O(n), where n represents the number of nodes in the binary tree. Let's break this down step by step. First, during initialization, adding the root node to the queue is a constant time operation, O(1). Next, the while loop processes each node exactly once. Within each iteration, removing the node from the front of the queue using queue.popleft also takes constant time, O(1), as this is a feature of the deep data structure. Additionally, appending the left and right child nodes of the current node to the queue, if they exist, requires O(1) time for each operation. This means that for every node, we perform a constant amount of work, and since there are n nodes in the binary tree, the total time spent traversing the tree is O(n). Finally, the return operation at the end of the algorithm, which simply returns either true or false, is a constant time operation, O(1). When we combine all of these steps, the traversal of the tree dominates the runtime, leading to a time complexity of O(n). The space complexity of the solution is O(n) in the worst case, where n is the number of nodes in the binary tree. This primarily arises from the usage of the queue. In the algorithm, the queue temporarily holds nodes that are yet to be processed. In the worst-case scenario, which occurs when the tree is complete, the largest level of the tree contains approximately half of all the nodes, or n/2. As a result, the queue can hold up to O(n) nodes at once. Moving on to other variables such as root, encountered_null, and node, these occupy a constant amount of space, O(1), regardless of the size of the tree. Therefore, the overall space complexity of the algorithm is dominated by the queue, resulting in O(n). Examining the best, average, and worst cases provides further insight into the algorithm's behavior. In the best case, where the tree is highly unbalanced, such as all nodes being on one side, the space complexity reduces to O height, where the height of the tree depends on its structure. For balanced trees, the height is log n, while for skewed trees, it can be as large as n. The time complexity, however, remains O(n), because all nodes still need to be processed. On average, most trees are not highly skewed, so the space complexity is typically O(n), and the time complexity remains O(n). In the worst case, when the tree is complete, the queue holds the maximum number of nodes at the last level, leading to both time and space complexities of O(n). Comparing this to a brute force approach, which might involve multiple traversals to count nodes, check depths, and verify node positions, the current solution is significantly more efficient. A brute force method would still have O(n) time complexity overall, but with higher computational overhead due to multiple passes. The current approach optimally achieves completeness verification in a single traversal. To formally justify the big O analysis, let's look at the key aspects of the algorithm. First, during the single traversal of the tree in the while loop, each node is processed exactly once. For each node, the operations performed, such as dequeuing it and adding its children to the queue, are all constant time operations. This confirms that the time complexity is O(n), where n is the total number of nodes. Next, the space complexity is determined by the maximum size of the queue. In the worst case, when the binary tree is complete, the queue can store up to n/2 nodes, which simplifies to O(n). Other variables, such as root and encountered_null, require only O(1) space. Therefore, the overall space complexity is dominated by the queue and is O(n). This mathematical breakdown validates both the time complexity and space complexity as O(n). When working with binary trees, there are a few common mistakes you should be aware of while checking for completeness. First, it's important to ensure that all levels of the tree, except the last, are fully filled. A common error is focusing only on the alignment of the last level while ignoring gaps in earlier levels, which is incorrect because completeness requires all prior levels to be full. Next, when using a level order traversal or BFS, some implementations fail to properly handle null nodes. Remember, once a null node is encountered, any subsequent nodes must also be null for the tree to be complete. If this order is violated, the tree does not meet the definition of completeness. Finally, there's a frequent misunderstanding between complete and full binary trees. A complete binary tree allows for nodes in the last level to be left aligned, while a full binary tree strictly requires every node to have either 0 or 2 children. Confusing the two can lead to rejecting valid complete trees or accepting invalid ones, so it's crucial to keep their definitions clear. Now, let's consider inefficiencies and edge cases. Some solutions traverse the tree multiple times, such as once to count the nodes and again for validation. This approach is computationally expensive and can significantly slow down performance for larger trees. Instead, aim for algorithms that consolidate these steps into a single traversal. Additionally, edge cases like an empty tree, a tree with only one node, or a tree with only left or right subtrees are often overlooked. These scenarios require careful handling to avoid breaking a naive implementation. From an interview perspective, it's important to understand the BFS pattern where completeness is verified by ensuring no nodes appear after a null node. This is a clean and intuitive method, but interviewers may also test your ability to optimize further, such as using index-based tracking. Be prepared to discuss trade-offs, such as the space complexity of BFS compared to other approaches like node count and recursion. Demonstrating your ability to handle edge cases thoroughly and communicate your thought process clearly is key to succeeding in these discussions. To deepen your understanding, there are several related problems worth exploring. LeetCode 958, the problem we're discussing, is the foundational exercise for checking completeness. LeetCode 222, which focuses on counting complete tree nodes, builds upon this understanding. Problems like LeetCode 101, the symmetric tree, and LeetCode 226, the invert binary tree, also emphasize tree traversal techniques that are highly relevant. Additionally, there are alternative approaches to solving completeness problems. One option is using node indices as if the tree were represented in a one-based array, similar to a heap. In this method, the last node's index in a complete tree should match the total node count. While this is more space efficient, it requires careful index management. Another strategy is the recursive depth-based approach, where you validate completeness by analyzing node positions relative to their depth and expected fullness. This approach avoids queue-based memory usage but can be less intuitive and harder to debug. Lastly, there's the two-pass approach, where one pass counts nodes and the second verifies alignment with DFS or BFS. Though easier to implement, it's less efficient than single-pass methods. Each of these approaches has its own trade-offs, so it's important to choose the one that best suits the problem constraints. Great job working through this problem. To summarize, we analyzed whether a binary tree is complete using a level-by-level traversal approach. This problem highlights the importance of understanding tree structures and traversal techniques. Thanks for your time, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!